So now let's take a look at proportions. Now proportions are simply a statement that says that two ratios are equal. So we're saying one fraction equal to another one. And how do we check to see if they're equal to each other? Cross products. So just like we did with fractions, we can cross multiply to see if those quantities are equal. And that means that the original fractions were equal. But how else could we use this? We can use this otherwise when we're trying to find one piece that's missing. So in this case, if we know a piece that's missing, we can still use this cross product property to find that missing piece with a little bit of algebra. So in this case, let's do the unknown cross product first. So we're going to get 4x equals 6 times 18. 6 times 18 looks like 108. And then we can get rid of the 4 by dividing. So it looks like 27. That's it. That's all you have to do. So set up your cross products, multiply and then divide, and you're done. Now, they can be a little bit trickier, like this next one. So now we got a little bit more substance to it. But the most important thing about this is to kind of pretend that there's parentheses around these more complicated tops or bottoms or just expressions in general. Put them in parentheses and then you'll be safer, and you'll see why. Well, it really doesn't matter which cross product we do first. Let's do this diagonal one here. I'm going to put the 11 out in front just to make it look a little bit prettier. So the 11 gets multiplied by the 3x minus 2. 5 gets multiplied by the 6x minus 5. So that would be your first step. But now how do we simplify those two sides? Why do you see those parentheses in there? Because we're going to have to distribute. We do want to distribute it to both parts of that expression. So 33x minus 22, 30x minus 25, parentheses are gone. Now what do? Now we got to move stuff around from one side to the next. So what did we say before? Let's start with the smaller of the two variable components and move that. So let's move the 30. And then we can cancel those. So that's going to give you 3x minus 22. And don't forget the minus sign. Bring down that minus 25. Now we can move this minus 22 by doing the opposite. So we got 3x equals negative 25 plus 22 is still going to be negative. So a negative 3. And now if we divide, oops, running out of paper. So x equals negative 1. Again, not anything too drastic, but you got to just be careful with those parentheses. If they're not there, it doesn't hurt to put them in, and you should be fine. All right, let's take a look at some other types of problems, like word ones. Haha, you thought we were done. But these ones are a little bit nicer than those other ones from 7.2. Those ones are pretty nasty. But these ones are not as bad. Because it's all revolving around proportions again. So 2 slices of bacon contain 85 calories. How many calories are in 12 slices? Now you might have your own ideas about how to do these quickly, and that's great. But if you're not sure, here's what I would recommend. Usually they try to relate two things that go together. So in this case, 2 slices of bacon contain 85 calories. Let's use that as one side of your proportion. So we got 2 over 85. But now the question is how do we set up the other side so that it works? Because it's not just a guaranteed setup. So it says how many calories are in 12 slices? So this is going to be our x. And then we got the 12. So where does the x go? Where does the 12 go? Well, it's going to have to be 12 over x. Now, why? Well, the units. The units are the key to this. If you write your units in, that will help you set up your proportion. So let's go back to the first one. 2 slices and 85 calories. So slices is on top, calories is on the bottom. So now you can see this is x calories and 12 slices. So slices. And that's always the way it's going to work. If you got one fraction equal to another one, the units have to be in the same spot on the other side, on both sides. So now that you know you set it up right, you don't need the units while you're doing the math, but you do need your units at the end. So now we can cross multiply. So we got the 2 times the x, we got the 85 times the 12. So 2x equals, and I'm going to make sure I do it right. So what's that going to be? 85 times 12 equals 1020. So now we can get rid of the 2. So x equals 510. So 510 what? 510 calories. Yeah, don't forget those calories. So think about that next time you eat 12 slices of bacon. Okay. What about other applications? Well, better buy. If you're buying stuff at the grocery store, how do you know which one's giving you the best bang for your buck? It's all based off of the unit price. So we're going to need the unit price. So how do we find that? Well, they're usually going to give you some quantity for some price. Some quantity for some price. Well, you got to put it into a ratio, but make sure you put it the right way. It's always going to be price over quantity. Price over quantity. So if you do that for both of those situations, you should be able to see which one's cheaper. So if we go to 249 over 20, we're going to get what? 2.49 divided by 20 equals 0.1245. Now that is going to be the price per ounce in this case. So again, a unit price needs a price and a quantity still attached to it, not just a decimal. Don't forget the units. So let's do the same thing. 429 over 30. So let's see what that equals. 4.29 divided by 30 equals 0.143. Now you're probably saying, well, wait a minute, this is money, right? Why do we need all those decimal places? Well, sometimes the unit prices are very, very close. So I would recommend doing 3, even 4 decimal places in some cases, just to make sure that they're not too close. But some cases, obviously, you can see pretty quickly that they're really far apart. Like this one here, we didn't need all 3 decimal places or 4 decimal places. This one's about 14 cents. This one's about 12 cents, 12 and a half. So this one's definitely cheaper. So there's our answer. 20 ounces of cereal for $2.49. All right, not too bad. Let's try one more, and then we'll stop this video. A doctor prescribed ampicillin for a child who weighs 9.1 kilograms. The label on the box recommends a daily dosage of 100 milligrams per kilogram of weight. How much ampicillin should the child receive per day? Now, some of you nursing students already know how to do this, which is great, but here's the mathematical way I would show you how to do it. What are you starting with? What comparison do we know right off the bat? We don't know how much medicine this 9.1 kilogram child needs, but we do know how many milligrams for 1 kilogram that we can give. So we got 100 milligrams over 1 kilogram. That's our starting point. We know That relationship has to stick. 100 milligrams for 1 kilogram. Now we could have wrote it the other way around, doesn't matter. But that's one side of your proportion. What's the other side going to have to look like so that way our units line up? You got it. 9.1 kilograms has to go on the bottom. And X milligrams would have to go on the top. So now we have our proportion. We don't need our units anymore while we're solving it. So let's set it up. Now this one's nice because it's 1 times X. Well, 1 times X better be X, right? And then we got 100 times 9.1. So X equals 910. So 910 milligrams. Now again, there's many mathematical ways that you can do these. You don't have to do them this way, but you do have to show some work of somehow of how you're doing it. So I don't want to see just answers on tests or anything like that. You need to show your work. So, all right, let's stop here and then we'll pick up the rest in the next video. See you soon.